Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about medical imaging, and in the last lecture we are discussing how the computed tomography could be carried out using X-ray images. So, we will discuss today also another technique which is called algebraic reconstruction technique. If you remember, in the last class we discussed Fourier slice theorem based technique and then filtered back projection technique. Now, in this algebraic reconstruction technique, what we do, we solve a system of linear equations, because we are getting line integrals. Now, each line integral can be expressed as a linear equation, and since you have a set of line integrals for a cross section, so you are getting a set of linear equations which you can solve to get the functional value. So, let me elaborate a bit. So, you can use these equations, as you can see that in the familiar form of linear equation. A is given its set of coefficients, and x is the functional values along that particular cross section, and p is the respective value of line integral. So, so the set of pixels or voxels of the image represented by a column vector. So, that is what you are considering. So, in this case we are assuming the two-dimensional function, they are linearized in the form of a one-dimensional function, and x is that function. So, again you can rearrange them to make them as a two-dimensional function or three-dimensional functions. So, actually this algebraic reconstruction technique, it can also perform volume reconstruction, because what it considers an equation means it is basically a line integral only. That forms an equation, whether the line lies only on a plane or over three-dimensional volume, it does not matter. So, that is the flexibility you have in this approach, and we will see that is why it is more generally applicable for image reconstruction. So, as I mentioned, each line integral in this case provides an equation. So, a row of this matrix A, it is found by the coefficients of the equation, and which means that if the point is already in the line, if this coefficient is 1, otherwise it is 0. So, any line integral means that this functional value. So, we are going to find out this functional value, which is expressed now as a variable, say x1, say this is x2. So, these are variable, and we are adding them. This is the line integral, we are adding them to get a value, say s. So, this is the equation. So, what we can consider, that if I have these variables, if I represent in the form of a vector, and there is certain positions x1, then suppose this is x2, this is x3, this is in the linearized form, if I get its respective position. So, in the equation, in this line integral, there is a row which corresponds to this line integral. So, x1 corresponding, the position of x1, the corresponding column which is responsible for denoting x1, it is an indicator function, there it would be 1. Similarly, x2, there it would be 1, but rest of them will be 0. And this is that aij's, which means it is the ith row, ith equation, and j is the respective, j is the column which denotes the respective variable of the functional space. And usually, as you understand, it is an overdetermined set of equations, because if there are, say, n pixels, you can get more than that the line integrals, and so it could be overdetermined set of equations. So, which means that you can apply the least squares method, and you can solve this problem using least squares method. It is a familiar form, as you can see that from this you can get A transpose A inverse A transpose P. Just to once again, just to show you how we derive it, earlier also I have mentioned that there is a nice way of getting this expression. So, you pre-multiply with A transpose both the side, and then you get A transpose A inverse A transpose P. That is how we get it. But this is the least square estimate, as I mentioned, that in the overdetermined set of equations, it's a rank deficient matrix. But when you have A transpose A, it's a square matrix. But the problem is that the dimension of X is very large, that 3-dimensional image or even the cross sections. So, that is why the respective inversion also will be costly. So, and in fact, it is not feasible. So, what we do, that there is a method which is called Kuss-Merz method by the name of the mathematician who has proposed it. So, in this method, iteratively we solve this one. So, as you know that each equation, it gives a hyperplane. So, and your solution would be the intersection of hyperplane. So, each equation itself is a hyperplane in the space. And so, just to in 2-dimensional, it means that if I have only 2 variables x1 and x2, say you have 2 variables only. So, you have these line integrals here, and you can have another line integrals. Of course, you can have more than 2 variables, say here, and but they are basically the hyperplanes. For 2-dimension, there is a 2 straight line which the intersection can give you this point. So, you can have 2 equations and you can get that intersection, and that is the solution in the straight lines. But in 3-dimension, you have the planes. So, you have equations involving 3 variables, a2 x2, say a3 x3, say equal to some value, say p1. Similarly, b1 x1, like this. So, each one is a plane in 3-dimension, and their intersection, this plane intersection, will give you the point, and that is the solution. So, ideally, if there is no noise in the data, you will get the intersection to a point. But what happens usually, there are noise, so they won't exactly intersect at a point. But in Kuss-Merz method, it takes care of that part. So, what it does, it starts with any particular value. So, let me consider, suppose you have, let me give you the example with respect to 2-dimensional hyperplane. So, suppose these are the two lines which are hyperplane. Now, you start with any point, this is the initial point, say P0. Then what you do, you orthogonally project on one of them, right. So, now this is your next solution, this is your next iteration. So, you moved it. So, you are trying to basically, the thing is that if it is in the solution, through orthogonal projections, you are coming through this intersection, but this also you orthogonally project for the next line. So, you orthogonally project to the next line. Then alternatively, you do that, and finally, it will converge to this solution. So, you extend it in the n-dimensional, in a general situation. And this orthogonal projection geometrically can be shown in this way, that when you have a point, say this is a hyperplane given whose normal is given by this AI vector is the normal. So, if I write, for example, AI transpose X equal to some value, say Pi. Now, this is a hyperplane whose normal is along AI. So, if you have a point here xk, if I orthogonally project, which means my point should move because this distance is Pi. So, the vector, say this is a vector from the origin, this is x. So, it should move along this direction. So, you should plus. So, this plus this will the movement towards this. That is what you are doing. You are moving along the unit vector. This is a unit vector. AI transpose AI transpose is unit vector. You are moving along this, and the amount of movement would be basically the distance of this point. So this is the distance of pi. This is distance of xk from the hyperplane. So this is very well known from the coordinate geometries. So this is what is projection, and you go on doing it alternatively for every hyperplane, and finally you stop at the converged point. So the advantage here is that it is applicable in general. So even for cone beam CT, where you take the projections, if you remember the cone beam CT, you are basically forming cone beams as X-ray, and then you are taking a planar projection of the object. Since you are now considering rays along the cone beam, so along each ray it forms a linear equations, and even in 3 dimension, directly in 3 dimension, you can solve this problem. So that is why it is more generally applicable methodology. So a typical CT, X-ray CT cross section of human brain is shown here. You can see this example. As you can see that this is one view. Of course, this is also X-ray CT view, and this is called sagittal view, and this is actually the axial view, that is the cross section view. So if I take any particular cross section along this line, and now you consider this plane, along this plane if I observe it, so it would look like this. That is how the CT cross sections are taken. Just for your information, it is a CT cross section of an 18-year-old male with no injuries presented in the axial plane with 4 millimeter slice thickness. And another example, typical example for a CBCT image. CBCT images are of low resolution, and they use also low energy. That is the advantage they have. So it's once again it's a cross section of pelvis of a colorectal patient, which is taken during radiotherapy, and these are certain values. The dimensions it has shown. It is a volume is in absolute dimension 450 into 450 into 157.5 millimeter. That is the volume, and this many number of voxels are taken. And whereas the cross sectional in the z axis is 2.5 millimeter. So that was the computed tomography X-ray images. But other than X-ray tomography, there are other forms of tomography is also available, where the physics behind this line integration is quite different. And this is one such tomography that we will be discussing, and this is called emission tomography. Actually, it is used for nuclear medicine, where the emission of the radiation from the isotopes, those are used to detect the respective concentration of doses along the tissues. So this is what, so that's why in this case the radiation source is within the body. Say X-ray was an external radiation, from externally X-ray is given to the body, and it passes through our body and then it produces an image. Whereas here emission tomography, the radiation doses which are radioisotopes which are injected in the body, and then our metabolic system, it digests those material, and there is a concentration at in different parts of the tissues. So the objective here is to observe, is to visualize the variations of those concentrations or distributions of those concentrations over that 3-dimensional space, because we would like to observe the functional behavior of different organs. So also we call it functional imaging. We call it nuclear medicine. So there are different terms. We also call it emission tomography. So as I mentioned, it is not from the outside as like CT X-ray. And there are different kinds of radioisotopes which we use. Here, for example, for phosphorus, there is an isotope 32p15. You know that 15 is the atomic number. This many number of protons are there, and 32 is the mass number, which means it has 15 protons and 17 neutrons. And this is one isotope. right? There could be another form of phosphorus where you can have a different mass number. So, but this isotope has a property, why it is called radioisotope, because it can decay spontaneously. There is also another popular isotope which is called technetium, which has, whose atomic symbol is Tc, right? So, and this 43 is its atomic number and 99 is its mass number, and this is the fluorine 18F9. So, this is also another isotopes. So, as I mentioned that it has to be injected. So, it is pushed as a dye of a compound of the isotope. It is not that that element is pushed, but there is a compound which contains that element. For example, 99M Tc ethyl cysteinate dimer, ECD. This is the form which is more convenient to name it. And the another one is fluorodeoxyglucose or FDG. So, these are different kinds of compounds which are injected, or dye we say, which are injected in the body, and they take some time to get digested, and then it gets distributed over the body with certain distributions. Mostly the uniform distribution is expected, but in some cases some of the cells, there could be heavy concentrations, and those are the indications of certain reasons why they are doing certain diseases or certain behavior of our response of our body system. There are two types of phenomena primarily which are responsible for this emission tomography. One phenomena is called single photon emission. So, it means that when this radioisotope, a nucleus of the radioisotope gets decayed, it radiates a photon, so we call it gamma ray, right? And it is a single photon which gets there. So, every event here is considered, every event of decay is considered is the activity of this radioisotope, and this is a single photon emission event. On the other hand, there is another kind of emission which is called positron emission, where you can see that what this nucleus emits a positron, and this positron travels, and suppose there is another electron from some external place, it is also traveling along these directions, which is there nearby electron, and they get when they collided, that they produces actually energy. So, this matter gets transformed into energy, and in this case actually two photons are emitted in opposite directions with equal energy, where say 511 keV because of these electrons. So, with this amount of energy, so it is emitting two photons in opposite directions. So, this phenomena is also very interesting. Two photons after collision simultaneously detected in opposite direction. So, simultaneous detection of these photons can indicate that this positron emission took place, and that is the activity of radioisotope. So, the presence of radioisotopes are only detected by the detection of photons, either for single photon emission or for positron emission. So, the imaging which uses single photon emission, this is called SPECT, or single photon emission computed tomography. On the other hand, the imaging system which uses positron emission, that is called PET, or positron emission tomography. And as I mentioned, that this is meant for functional imaging for studying biological processes. So, let us have some ideas about what is meant by this radioactivity and how do you detect it. First thing, as I said, it is a spontaneous process, it is a stochastic process by which an unstable atomic nucleus loses energy, and it basically radiates subatomic particles. So, that is the phenomena of radioactivity, and this process is modeled by a Poisson process. So, the stochastic process with mean and variance lambda. So, there is a probability, it follows a probability distribution, the time interval, it follows a probability, or rather I should say number, rate, this rate. So, number of emission at a particular interval, it follows that. So, so this is a you can say the probability distribution, that with the rate lambda, this is the mean, and with variance lambda, this is a Poisson distribution. So, what is the number of emissions at a given observation? And its unit of radioactivity we expressed in terms of that is, the name is Becquerel. Becquerel is a famous French scientist who discovered radioactivity, and honoring them, this name is unit has been proposed, has been used, and it is very simple unit. That is, as I mentioned, it's a kind of discrete event, that emission of a single photon or emission of basically 2 photons, simultaneous emission 2 photons. That is the observation you have for positron emission. So, it is 1 disintegration per second. So, one such event, whether it is 1 photon or whether it is 2 photon, one such emission, one such event per second. So, something like unit of a frequency, you can say. So, patient dose typically ranging from 100 to 1000 megabecquerel. So, you see that it is a very small unit, and your power of the isotope, or rather the activity, amount of activity is expressed by this unit. Higher this unit, higher the amount of radiation, radioactive dose. And there is a particular process by which this decay takes place, and that is also it follows an exponential decay, and there is a half lifetime period. That means the time interval when the intensity of this amount of this radioactivities, it gets halved over that time. So, every time interval, it will be half of the total activity will be half of that. So, the number of emissions will be reduced by half after that half life. There is a half life time period for every radioisotope it is mentioned. So, for example, for this technetium, so we have this that 100 megabecquerel sample of radioisotopes, we have a half life of 6 hours. Say this is a very typical example, which means that if you note that this radioactivity level at 100, which means 100 disintegration per second. So, after 6 hours, it would be 50. That sample would radiate 50 in number per second. Then after another 6 hours, it would be 25. In this way, it gets decayed, and it follows an exponential decay. So, here for a single photon emission tomography, computed tomography, we follow this principle that there is a detector which detects this radiation, and that since it detects this gamma ray, we call it gamma detector. So, this array of detectors, it detects this, and what is required, that since you are doing tomography, the directionality is important. So, for that we use something like collimator, which controls the direction of this detection. So, this detector knows that all this emission is coming in this line. Similarly, for every position, there has to be some kind of collimation from where it is collecting this radiation. There could be some interferences, but we may ignore, or we have to take care of statistically that part when we do the better reconstruction. So, the disease detector, they record the average number of emissions of gamma photons at a given time. So, this is what it is considering, because you have radioisotopes along all these lines, their concentration. So, you get a line integral. So, this is how this line integral is coming here, and then you apply the standard technique of computed tomography, particularly algebraic reconstruction technique would be more suitable here, which is followed, and we can form the respective image using computed tomography. So, there are two modalities we have mentioned because of two types of emission that we considered, single photon emission and positron emission. Accordingly, we have devices based on single photon emission, which is called SPECT or single photon emission computed tomography, and then again positron emission tomography or PET. So, the SPECT has a detector array and it is one example how this detector array is designed. You can see that those are the array of collimators, because they are passing in the rays along that line, and there are actually photomultiplier arrays are also there, which means this is very weak, so you need some kind of amplification. So it multiplies those photons, so then you get detection. So this is just a schematic representation of a gamma camera showing three primary components. One is this collimator, another one you can see NaL crystal, and this PMT array. Whereas in the positron emission tomography, we have ring detector. What happens that it is traveling into opposite direction, so there would be two detectors which will be detecting those opposite rays. So something like this. So the simultaneous detection is the key here. So once we record a simultaneous detection, then only we consider this is the positron emission. Otherwise, if there is no simultaneous detection, we may consider them as a noise, and it would give you a better noise handling capabilities. So this simultaneous monitoring of signals from each detector block and record counts when an impulse is detected from two blocks at the same time. So these are the detector blocks, and only we record counts when the simultaneous detection is possible. So there are methods like algebraic reconstruction technique. I mean, there is actually statistical analysis like maximum likelihood estimate of those this array, this attenuation, these coefficients, the count, that what is the radioactivity concentrations or radioactivities doses at those points, the concentrations. Now those are estimated using this method. So when we reconstruct this image, we have seen for X-ray imaging also, we convert it or CT X-ray, we convert it into an Hounsfield unit. But here also we can calibrate these devices to convert those units, those recordings, those values into an absolute form of the dose concentration. Suppose the kilobecquerel per milliliter. That is so for that you require strict calibration. So we can use some phantoms. In medical devices, you can build up certain phantoms mimicking certain tissue properties. Those are the gels. These are certain things you can do, and then you take the image and you observe those measurements, like either the phenomena of positron emissions or SPECT, and then for that device you calibrate with the concentrations of doses. So you inject doses with known concentration and then you observe them, and you can get the respective calibration. So you compute the volumetric sensitivity, like alpha volume is counts per minutes and to milliliter per milliliter divided by kBq per milliliter. That is the dose concentrations. There is another unit which is also used in many cases for the analysis, that is called standardized uptake value, and which is normalized by patient's weight and dose. So this is how you see that these values are expressed. This is a volume of interest. So what is the amount of dose in absolute sense per milliliter, and then what is the the dose MBQ injected, total amount of dose injected, and also the weight of the person, and that gives you it expresses the respective concentration in terms of SUV, and which helps in the diagnostic purposes. And you can normalize it also by the maximum SUV that you can observe at that in the image. So some of the assumptions here, that tracer gets distributed uniformly in healthy tissues, and density of body is equal to density of water, which is 1 kg per liter. The interpretation is that if this standardized uptake value is significantly greater than 1, then it indicates disproportionate amount of uptake and abnormal activity. Now, there are imaging systems which takes care of, which shows both functional and anatomical perspectives of a subject. That means we call it hybrid imaging. You can see here that it's a combination of CT and PET. So this portion is meant for capturing CT image cross sections, and this portion is PET, and there is a platform which slides from in this direction. So the subject is moving in these directions, and when it moves, it captures the PET for this cross section. At that time, it is capturing CT for this volume. So in this way, the whole body scan you can make, and you can relate the CT and PET, and that gives more meaningful information. So some examples which you are showing here. Suppose this is the anatomical information just from the CT scan, and this is the functional imaging from the PET scan. And when we register them, co-register them, because anatomical registration already the control devices, and if I superimpose them, now this gives you the information of, you can see the different organs with different dose values, and from there it is possible to detect the any kind of diseases or any kind of behavior, functional behavior of organ. This is also another example. This is actually the SPECT. It is a differential SPECT scan, and this is FDG PET scan for a patient with melanoma. So we can see that even the small lesions are visible. So this is the power of this method. Now that was functional imaging, and using the emission tomography we can get images. Next, the kind of tomographic scan what we will be discussing, it is called magnetic resonance imaging. Now we don't, in this case we don't do we don't actually compute, we don't compute in the same way, reconstruct the images from projected values. Rather, here what we consider, we sense the magnetic behavior of tissues. We sense the magnetic polarizations, and from there is an interesting mechanism by which we can sense the distribution of magnetizations in the frequency space directly. So we will come to that principle. So to elaborate this part, first thing, that there are magnetic needles in our body. We should understand that we have lots of hydrogen ions in our body, and they act like a magnetic needle. So it's a vast number, 10 to the power 27. It's a huge number. So the spin of the nucleus makes them act like a magnet. So spin here is kind of rotation of nucleus. So it is a kind of easy way to visualize the spin in that fashion, and you know that it has a directionality, and that gives you the direction of magnetization. But since it is random, then this net magnetization is 0, right? You have random spin. But when in the presence of an external magnetic field, they get aligned. They get aligned with this, and then actually there is a net magnetization. Now this may not be exactly along the external magnetic field, but it will make some angle, and what it would do, rather it would be rotating around that. It's like a like a toy top, which is which we just rotate using a thread, and then we can see that top is rotating along the vertical axis and slowly coming towards getting aligned to that vertical axis. So because it is due to random interactions among nuclei, the alignment is partial, as I mentioned. So this is what. So suppose this is the net magnetization, but it is not static. It is basically rotating like a top, and it is basically going getting aligned in some directions, or with some making some angle, it is rotating. So that is a kind of phenomena what happens during these magnetizations. But we will talk about this net magnetization, and this net magnetization that actually provides you some information, and there is a phenomena called magnetic resonance, which actually gives you quite interesting information. So this rotation of magnetic field is called precession. So, and this frequency of precession, it is proportional to the inducing magnetic field, what is B naught. Like this is the relationships, and this is a very interesting relationships, which is called which you can show that this frequency is called Larmor frequency, and which is proportional to this B naught, strength of this B naught, and this gamma is called gyromagnetic ratio. So these are all dependent on the kind of material you have. Say for example, we have this hydrogen ion. So for hydrogen ion, this value is 42.5676 megahertz per Tesla. Tesla is the strength of the magnetic field. And then Larmor frequency for hydrogen ion is 64 megahertz at the when 1.5 Tesla is applied there. So we can see here that given this magnetic field, there is a particular frequency on which actually this rotation takes place. So this is what is magnetic resonance, and this information is very crucial, this is the key information which is used for sensing the magnetization. Because when it is rotating, you know that it also radiates energy. So a rotating magnetic field, it radiates energy, and that radiation also has a frequency, and which is equal to the Larmor frequency or resonant frequency. So now this you can detect, this radiation you can detect, and you can get those distributions. But we do something more for that. So one is that you can detect the M modified by weaker magnetic field. So if I apply a weaker magnetic field orthogonal to B naught, what happens that this magnetic field, so before excitation it was like this, but after applying this magnetic field, it will get aligned with this direction. So from this it will basically come to this. I mean, if I observe as if it is a rotating turntable, and because it was rotating, so it is basically its polarization, its direction will be changing from vertical direction to a direction over this turntable plane. Now, so this is how it takes place when there is an orthogonal magnetic field. That happens here. But when you apply this orthogonal magnetic field, because you are exciting it, it has to be in the resonant frequency. So resonant frequency, because at this magnetization, external magnetic field, there is a resonant frequency, and if this field varies with resonant frequency, then only it gets excited. Otherwise, it does not get excited. That is what it happens. And then after, if I withdraw this magnetic field, then once again, it goes back to the place, and we call that process as relaxation. So this was excitation, and then the other one is relaxation. So after relaxation, it gets also aligned with that. So what happens there? In that case, there are two components, as you see at each point there are two components. One is transversal component, another one is longitudinal components. So it gets transferred, this transversal component gets transferred to longitudinal component. So in the relaxation process, this transversal component decays, while longitudinal components it actually recovers. So this is the process. While for excitation, the longitudinal components decays and it gains the transversal component. But excitation is faster. Excitation is very fast, and relaxation is slower process. So that is one thing. So this is a faster process, and the relaxation is a slower process. But while doing these things, once again, during relaxation, it also emits the radiation, and this frequency would be also the Larmor frequencies. So you can detect this radiation, and by detecting this radiation, and you can find out that how much of magnetization is there. Amount of radiation will be based on that. So the polarized RF radiation detected at Larmor frequency. But one of the thing, as you can see here, like in previous cases of tomographic scan, there was a directionality which was involved in sensing the contrast of tomographic scan. In contrast to tomographic scan, in sensing this, there is no directionality involved. Now, let us also understand the nature of decay and recovery of magnetization components. So, as you see that longitudinal components, it recovers exponentially with a time constant T1. So, there are two different time behavior of this longitudinal and transversal components. Say, it gains with a time constant T1. So, when it is relaxed, the longitudinal component, it recovers from 0 to the original state of its magnetization. Whereas for the relaxation component, transversal component, it decays from its induced from that transversal component because of the excitation, and it has a separate time constant. One is called T1, and this is called T2. So, this phenomena is called T1 relaxation, and this decay is also called T2 relaxation. So, decay of transversal component is T2 relaxation, and gain of recovery of the longitudinal component is called T1 relaxation. Now, this T1 and T2, these are the parameters which varies over the tissue property. And another thing here also, so actually there is a theoretical decay because of the tissue property, but in practice it is faster than theoretical, but no, that can be compensated. So, as I mentioned, T1 and T2 depends on tissue properties. In particular, say these two curves which you are showing here with the time constant, say 2.5 second for the recovery period of longitudinal component, and 45 millisecond is the decay of transversal component. As you can see that this is a slow process, recovery is slow process, but decay is very fast process. So, by this time constant you can see. But this is for arterial blood. But if you have any other tissue, these values will vary. So, when we consider the contrast imaging using magnetic resonance imaging, we are actually trying to get contrast of this time constant. So, at certain times, when we take the image, because of the variation of time constant, the amount of magnetization will vary. And that would indicate different kinds of anatomical variations. So, that is what now we have T1 weighting images and we have T2 weighting images, and there is another mode which is called proton density weighting. So, in T1 weighting, the contrasts due to recovery of longitudinal component, those are used, contrasts among the materials, among the tissues like bone, arterial blood, etc. And for T2 weighting, the contrast due to recovery of transversal component, those are used. Whereas for proton density weighting, it is simply the variations due to the proton density. Proton is that hydrogen ion, and it is a tissue specific property quantifying the number of mobile hydrogen protons per unit volume. So, there are three such modes of imaging, and there are two imaging control parameters by which actually this T1 weighting, T2 weighting, or three such modes could be selected. Let us understand those two parameters. One parameter is called echo time parameter. So, it is the time delay between the between excitation and measurement. So, when you are exciting the magnetic field with exciting a tissue, the net magnetization it would go from longitudinal component to the transversal component. That is the excitation. Now, when you excite and then after that you measure, that means you are measuring, actually it is after withdrawing it you are measuring. So, that is the time. So, after excitation then you are withdrawing and then you are measuring. So, the whole thing is a time delay, and depending upon, if you measure say too fast, then as you see that your recovery will not be very high. So, since your recovery will be slower, so you have more T1 contrast, because the variations that would be observable. But if you, so this is what we will see that, and the repetition time is that when you are doing it repeatedly, what is the next time of excitation from one period of excitation. So period of one time is the next time is of excitation. So that means that time indicates at which point you are measuring it. So as you see that longer longer echo time will have a better contrast for T2 images, but it will have a weaker signal, because in longer echo time what happens that it is decaying fast, so it will be mostly decayed. So depending upon the T2 contrast, the decay amount will vary, but the signal will be weaker. So the behavior would be more observed because of this T2 time. So in the beginning it will not be observed. If it is shorter, it will not be observed. On the other hand, shorter echo time, or if I say shorter TR, better contrast for T1s. That means if I have excitation, so we are not recovering, we are not giving full recovery. So your signal is weak, but still the variation of T1 will give you the variation with the contrast among the volume. So this is the summary. If you have short TR but short TE, this is T1 weighting. We understand that short TR and also echo time is also, measurement time is also short. So accumulation of recovery is not full, recovery is partial, and you get better contrast, though the signal is weaker. On the other hand, for longer TR, that repetition time, and also longer echo time, you get T2 weighting, because most of the decay takes place by that time. Most of the decay takes place by that time, and in such a case, your T1 will not have that kind of contrast. But if I use the transversal, when you are measuring the polarized sensation. Either you are measuring transversal field or longitudinal field, but your T2 will have the respective contrast. And if you have a short echo time and long TR, then the effect of both recovery and decay, those are not making any contrast, but net magnetization varying over the tissues will be reflected, and that is called proton density weighting mode. But this is a mixed mode where you cannot get any conclusive contrast, you cannot isolate a particular phenomena. So these are the three modes by which this nuclear magnetic resonance imaging takes place. So now let us consider that how do you locate the source of magnetization, because you can sense the magnetization by a detector, the amount of magnetization, but it does not tell you that from a volume from which point this magnetization is coming. It could be from the whole body, then there is no possibility of resolving the source. So for that we use the phenomena of magnetic resonance. So what we do, we use the gradient coils for having the spatial variations for exciting the magnetic field. So here we use 3 gradient coils along 3 orthogonal directions. Like if I consider this schematic diagram, so we consider, say, this is the Z directions, because it is a cylindrical along which a subject is lying. So this is, say, Z directions, and that this is a magnet which, say, causes the magnetization B0 along Z directions. This is a gradient coil, and there are 3 gradient coils. So along Z direction also it, say, causes a spatial variations of magnetic field. So on top of that, so we can write, say, they say this gradient field as B0, say, plus Z, right. So this we can write in this way. And of course there is also another radio frequency coil, RF coil, which will excite the magnetizations as you see that to provide these kind of transverse magnetizations. Now so this is the B0 is showing, this is the direction. So first we do the slice selection. That means, as you see that because of the spatial variation, there is a particular frequency for a particular value of Z, that is the Larmor's frequency. So if I resonate, if I excite the respective device with that frequency, so a particular value at particular value of Z, the magnetic induction will, that transverse component at that points only, the longitudinal magnetic field will be excited to become the transverse magnetic field. So that phenomenon will be restricted along that cross section. So when you observe any measurements, these measurements should be related to that cross section only. But this is only, this is still not resolving the two-dimensional distributions. So for that, what you do, that we sense the spatial distribution by considering a two-dimensional sinusoidal variation of the magnetic field, and then it performs the correlation. That means it performs the inner product. So that induces. So basically, this is called the phase measurement. So whenever they are in phase with that variation, that gets amplified, that gets accumulated. The out of phase, it gets basically suppressed, and I mean, that is negative. That negative. So in phases are only accumulated there. So in this way, you get the, it's a kind of inner product of a sinusoid with the function. So which means that you are actually sensing the frequency spectrum component at that point. So this is what we are sensing, a frequency component, and this measurement is called K-space measurement, because K is a frequency, indicates the frequency value in the digital domain. So directly three-dimensional sinusoid may be used for volume selective sensing in K-space. So just to tell about this K-space imaging, we sense in the frequency space, and by this we obtain two-dimensional and three-dimensional Fourier spectrum directly. So this is one such examples that we are actually sensing different sampled values of frequency components by using those gradient coils, by simulating the distribution of magnetic fields over space, inducing magnetic fields over space. First you select the cross section, and then have the two-dimensional spatial distribution of magnetic fields, and then you get the frequency components along that cross section. So Kx, Ky as a 2D cross sectional. For 3D, again, you can directly have that three-dimensional sinusoid and get exactly the respective frequency component. So once you have this, from this K space, then from there you can apply the inverse Fourier transform to get the images. So some examples of MR images, magnetic resonance images, you can see that this is T1 enhanced image and this is T2 image. This is basically T1 contrast and T2 contrast. As you can see that, different tissues are, they behave differently under this two relaxation process. So the last imaging modality I will briefly discuss, that is about ultrasound imaging modality, where we perform imaging through reflection of sound wave. So in this case, what happens that in our body, suppose there is something inside within the body, the object, and then there is a piezoelectric transmitter which generates the sound wave. So it acts both transmission as this. So it's a transducer and also transducer. It basically transforms electrical energy into sound energy. Again, it converts back. So this is what these are piezoelectric crystals that performs this. So once these acoustic waves, they are basically transmitted and then they get reflected from the body, and those are received, and part of it also gets transmitted. So this reflection, from the reflection we can get the, we can measure the distance of the object, and also the amount of reflection can give you the corresponding tissue property. And you see that this is very cost effective, and also since it does not require any kind of radiations, ionizing radiations, so it is more safe to use. So it measures the depth and reflectivity of the boundary surface between two media. And in some mode, even the shift of frequency, suppose this body is moving, so this reflected wave will have a shifted frequency like Doppler effect, we call it Doppler frequency. From there you can, by the shift you can measure the velocity of the target object also. So the temporal dynamics of objects also could be captured through this imaging, and this operates between 2 to 40 megahertz of acoustic wave. So you know that the sound wave, it could be characterized by some of these parameters like intensity, frequency, its velocity, wavelength, where wavelength and frequency and velocity they are related. This is a very well known equation. Also the attenuation also takes place in the same format to what we discussed for Lambert-Beer's law. It is also observed here, and the fact is that if you have higher frequency, you have higher attenuation, so that's why you have lower penetration. That is for the higher frequency part, but the resolution will, once again, the resolution will be better for higher frequency because your wavelength is small. So the axial resolution will be better because there is lambda by 2, so the wavelength is smaller, the wavelength axial resolution, because the interference, reflected waves interference will be less. And the lateral resolutions, because in some mode we also scan the body with these acoustic waves laterally. So then the lateral resolutions, because these reflections also will be spreaded, and practically the 3 lambda is a lateral resolution, which means if you have higher frequency, you have better resolution but low penetration. There are 3 modes of ultrasound imaging. One mode is called amplitude mode, where the height of the amplitude of the reflected ultrasound is displayed over the sonic runtime in the sonic ray direction. So you just during runtime only in one path itself you trace the ultrasound reflected beams, and from there you understand the structure just at the path. In the brightness mode, you scan it, you scan it over the 2-dimensional space, so you get the 2D structure. So for each scan, there is also another mode called motion mode or M mode, where actually this temporal variation is also plotted over time. So the stack of this temporal scan, so that would give you the temporal variation profile of a particular object at that particular point. So it forms a 2-dimensional image. And Doppler mode is primarily measures blood velocity using Doppler shift of the frequency of reflection. So these are few examples of ultrasound imaging. It's high resolution, which means it uses higher frequency, but its penetration is less. And this is a colored Doppler, so you can observe that this color code, actually this is a pseudo color code. So it is basically given by the device manufacturer. This code is used, and there is a standard code by which physicians, they understand the speed. So when it was towards sensor, then actually your code is, you have the higher velocity towards sensor, your frequency will be increasing. So you will be having blue color, and away from the sensor will be red with in the opposite directions. So just to summarize that what we discussed under the topic of medical imaging, we discussed about various modalities of medical imaging, like we discussed about X-ray, then computed tomography, and computed tomography using X-ray. Again, there are emission tomography, where we have single photon emission computed tomography, positron emission tomography. Then we discussed about magnetic resonance imaging, and finally we discussed about ultrasound imaging. So with this, let me conclude my lecture here. Thank you very much for your listening and patience.